Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Episode 4 taught you EKS multi-cluster fundamentals, independent clusters per region, no federation, cross-cluster service discovery via DNS or service mesh. We touched on service mesh briefly. Today, we're going deep on Istio multi-cluster for teams that actually need it. Here's the reality check. Most teams don't need service mesh. DNS-based failover with Route 53 works fine for hot-warm architectures. 2-minute failover is acceptable. But if you need hot active-active with subsecond failover between regions, service mesh solves problems DNS cannot. Today, you're learning Istio multi-cluster mesh in production. Not the getting started tutorial. The real implementation with all the operational complexity. By the end of this lesson, you'll understand Istio multi-primary configuration for multi-region EKS, how Envoy sidecars route intelligently between clusters, virtual services for progressive traffic shifting, circuit breakers and retries for reliability, and the critical question, is the operational complexity worth it for your team maturity? Let's start with what service mesh actually gives you beyond DNS failover. DNS failover, from Episode 8, Route 53 health checks detect failure in 90 seconds. DNS TTL adds another 60 seconds. Total failover time, 2.5 minutes. During that time, users see errors. Service mesh failover. Envoy sidecar proxies detect backend failures within seconds via health checks and circuit breakers. Automatically route to healthy backends in another region. No DNS involved. No TTL wait. Subsecond failover. But here's the cost. Every pod in your cluster gets an Envoy sidecar, consuming 128 to 256 megabytes memory and 0.1 CPU. For 100 pods, that's 12 to 25 gigabytes memory and 10 CPUs just for sidecars, plus the Istio control plane consuming additional resources, plus operational complexity, mesh upgrades, certificate management, debugging, distributed tracing issues. Is it worth it? Depends on your RTO requirements and team maturity. Istio multi-cluster architecture comes in 3 flavors. Multi-primary, where each cluster has its own Istio control plane. Primary remote, where one cluster has the control plane, others are remote. And multi-network variations for clusters that can't route pod IPs directly. For multi-region, use multi-primary. Each region's EKS cluster gets its own Istio control plane. This provides resilience. If one region's control plane fails, other regions continue operating. The control planes share configuration via multi-cluster secrets. Installation steps. First, install Istio in each EKS cluster using Istio.htl. Configure multi-primary mode with a shared trust domain. Create a common root CA certificate authority that all clusters trust. This enables mutual TLS between services across clusters. Second, expose Istio ingress gateways in each cluster. These gateways allow cross-cluster traffic. Services in US East 1 reach services in US West 2 by routing through gateways. Third, configure cross-cluster service discovery. Install remote secrets that tell each cluster about other clusters, API servers. Now services can discover endpoints across clusters automatically. Configuration example. You've got a checkout service running in both US East 1 and US West 2. Without service mesh, you'd use DNS with health checks. With Istio, you create a virtual service that defines routing rules. Virtual service splits traffic by percentage. 90% to US East 1, 10% to US West 2 for gradual migration, or 50-50 for active-active load distribution. or 100% to the closest region based on locality. Envoy sidecars handle this automatically. A front-end pod in US East 1 makes a request to the checkout service. Envoy intercepts, checks the virtual service rules, routes 90% to local US East 1 checkout pods, and 10% to US West 2 checkout pods via the ingress gateway. Locality-aware routing is the killer feature. Envoy preferentially routes to the local cluster first for the lowest latency. Only routes to the remote cluster when the local cluster has no healthy endpoints. This keeps most traffic within the region, minimizing cross-region data transfer costs from Episode 9. Circuit breakers prevent cascading failures. You configure maximum connections, pending requests, and retries. When the US West 2 checkout service starts failing error rate above a threshold, the circuit breaker opens. Envoy stops sending traffic there immediately. No DNS health check wait, no TTL propagation delay. After the circuit opens, Envoy periodically attempts requests to test if the service has recovered. When the error rate drops below the threshold, the circuit closes and traffic resumes. This happens automatically at the request level. Retries add reliability. Envoy can retry failed requests automatically with exponential backoff. A request to US West 2 times out, Envoy retries to US East 1. The application doesn't see the failure. This masks transient network issues. Real production example: a microservices e-commerce platform. Checkout, inventory, payment, notification services, all running in US East 1 and US West 2. Istio multi-primary mesh connecting them. Normal operation. A front-end in US East 1 calls the checkout service. Envoy routes to local US East 1 checkout pods. Checkout calls the inventory service, routed locally. Inventory calls DynamoDB, local region. Total latency, 50 milliseconds, all in region. During a partial failure, the US East 1 inventory service pods crash due to a bad deployment. Envoy detects a high error rate. The circuit breaker opens. New requests from the checkout service automatically route to the US West 2 inventory service via the ingress gateway. The cross-region call adds 150 milliseconds of latency, but the requests succeed. Users don't notice the failure. Automatic recovery. Engineering rolls back the bad deployment. The US East 1 inventory pods become healthy. The circuit breaker closes after confirming a low error rate. Traffic automatically shifts back to the local pods. Total incident time, 3 minutes. 0 user visible errors. This is what Service Mesh enables. But it comes at an operational cost, operational complexity. Mesh upgrades require careful rollout. Upgrade the control plane, then the data plane sidecars. A rolling upgrade across hundreds of pods takes time. Get it wrong, and you break production traffic. Certificate management, mTLS between services, requires certificates. Istio manages certificates automatically via Cert Manager, but cert expiry can cause outages if not monitored. Certificates need rotation. The root CA needs secure storage. Debugging complexity. When requests fail, is it the application code, a network issue, the Envoy configuration, or a control plane problem? Distributed tracing with X-ray from Episode 7 becomes mandatory. Without tracing, debugging is impossible. Resource overhead. 100 pods with sidecars adds 12 to 25 gigabytes of memory. For R6G.4 extra-large instances with 32 gigabytes, that's 30 to 40% of memory consumed by mesh infrastructure. You need to provision larger instances. Performance impact. Sidecar proxies add latency, typically 2 to 5 milliseconds per hop. For a request path touching 5 services, that's 10 to 25 milliseconds of added latency, usually acceptable but needs measurement. When to use Service Mesh? You need hot, active with automatic failover. You have a microservices architecture with many inter-service calls where a failure in one service shouldn't cascade. You have a platform team with Istio expertise or the budget to hire specialists. Your RTO requires Subsecond failover that DNS cannot provide. When not to use Service Mesh. You can achieve your RTO with DNS failover. Your team doesn't have service mesh experience and cannot invest in learning. Your architecture is monolithic or has few services where the mesh overhead isn't justified. Your traffic patterns are mostly external API calls, not internal service-to-service. For most teams building hot-warm architectures, DNS failover from Episode 8 is sufficient. A 5-minute RTO from Episode 2 doesn't require service mesh complexity, save the operational overhead. But for teams running hot at scale with strict availability requirements, service mesh pays off. Netflix, Uber, Airbnb use Istio in production for exactly this reason. They have dedicated platform teams maintaining the mesh. Alternative to a full service mesh. Start with DNS failover. Add service mesh incrementally to critical services only. Not every service needs a mesh. Checkout and payment services get the mesh for reliability. Internal admin tools stay on DNS. This reduces operational complexity while protecting revenue-critical paths. Common service mesh mistakes teams make. Mistake 1. Deploying a service mesh without understanding what problem it solves. Teams hear service mesh is best practice and deploy it. Then struggle with operational complexity for no benefit. Fix. Clearly define RTO requirements and evaluate if DNS failover is sufficient before adding a mesh. Mistake 2. Insufficient monitoring. A mesh adds another layer of infrastructure that can fail. Without monitoring Sidecar health, certificate expiry, control plane status, you're flying blind. Fix. Monitor Envoy metrics, set up alerts for certificate expiry, and have a dashboard showing mesh health. Mistake 3. Upgrading the mesh without testing. Istio upgrades can break traffic routing if not careful. Teams upgrade in production without testing and staging. Outage results. Fix. Test mesh upgrades and staging with production-like traffic first. Use a canary rollout for control plane upgrades. Mistake 4. Over-relying on the mesh for resilience. Teams think, we have a service mesh so our services don't need to handle failures. Wrong. Services still need timeouts, retries, and fallbacks in the code. A mesh adds another layer, but doesn't replace application-level resilience. Before we wrap up, pause and answer these questions. Question 1. You have a hot-warm architecture with a 5-minute RTO. Should you deploy an Istio service mesh? Question 2. Your microservices application has 100 pods. Each Envoy sidecar uses 200 megabytes of memory. What's the total memory overhead? Question 3. When does a service mesh provide value over DNS-based failover? Take a moment. Answers. Question 1. Probably not. A 5-minute RTO can be achieved with Route 53 failover from Episode 8. DNS health check detection of 90 seconds plus a TTL of 60 seconds equals 2.5 minutes, well within the 5-minute budget. Service mesh adds operational complexity for no RTO benefit, unless you have other requirements like internal traffic encryption or advanced routing policies. Question 2. 20 gigabytes. 100 pods times 200 megabytes equals 20,000 megabytes, which equals 20 gigabytes. Plus control plane overhead of another 1 to 2 gigabytes. You need to account for this when sizing instances. If your instances have 32 gigabytes of memory, the mesh consumes 60 to 70%. Question 3. When you need Subsecond failover that DNS cannot provide. When you have hot, active traffic patterns. When you need advanced traffic splitting like canary deployments across regions. When you need automatic circuit breaking and retries at the mesh level. And when you have the team expertise to operate it. Don't deploy a mesh just because it's trendy. Let's recap what we covered. First, Istio multi-cluster mesh connects independent EKS clusters at the service level. Envoy sidecars handle intelligent routing, circuit breaking, and retries. Subsecond failover compared to DNS's 2-minute failover. Second, multi-primary configuration gives each region its own control plane for resilience. A shared route CA enables mTLS. Ingress gateways allow cross-cluster traffic. Third, Locality-aware routing keeps traffic within a region when possible, minimizing data transfer costs. Circuit breakers automatically stop sending traffic to failing backends. Virtual services define traffic splitting policies. Fourth, operational complexity is significant. Mesh upgrades, certificate management, debugging distributed systems, resource overhead requires a dedicated platform team or expert. Fifth, use a service mesh when you need capabilities DNS cannot provide. Don't use it when simpler solutions work. Match complexity to actual requirements. Remember episode 4's independent cluster pattern? Service mesh builds on that foundation, adding cross-cluster service discovery and intelligent routing. But the independent cluster architecture remains. Each region has its own control plane, its own Istio deployment. We'll see service mesh in action in episode 12 during disaster recovery procedures. When you fail over from US East 1 to US West 2, how does Istio handle the traffic shift? How do you test mesh-based failover? Next time, disaster recovery, the actual procedures you execute at 2 a.m. You've built multi-region, you've tested it in staging. Now comes the real test, failing over during an actual outage without making things worse. You'll learn how to test DR without impacting production. Step-by-step Aurora promotion procedures, EKS, traffic shifting validation, rollback procedures when the failover goes sideways. Chaos engineering to validate your DR actually works, and the runbooks that save hours during incidents. Because your first failover shouldn't be during a real outage. Let's make sure you're ready. See you in episode 12.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.